6.2. It's factoring quadratic equations, and so if you thought that graphing a quadratic equation to find the roots maybe wasn't the best way and you just wanted to do some algebra instead, then you're in luck, okay, because that's what we're going to do here. And you will learn in physics, when you take physics 30, how common or how useful this kind of motion is. But football, soccer, basketball, and volleyball are just a few examples of sports that involve throwing, kicking, or striking a ball. And each time a ball or a projectile sails through the air, it follows a trajectory that can be modeled with a quadratic equation. Okay, so it just basically means that anytime you throw something, it's always going to follow basically the same mathematical equation. It's going to make a parabolic shape, and that's just due to the action of gravity. Okay, each of these sports is also played on a rectangular playing area, and you can also model the playing area for each sport by a quadratic equation. And that's something you might remember when we did the area of the corral, how that was a quadratic function. Okay, that was a few, one chapter back. Okay, so for women's indoor volleyball competition, the length of the court is twice its width. Okay, and so if x represents the width, then 2x represents the length. Okay, and you know that area equals length times width. And so that's going to be equal to 162. All right, so if you want to write that as a standard form quadratic equation, you'd have 2x squared minus 162 equals 0. Because you know you have to have ax squared plus bx plus c. So in this case, our b is equal to 0. We don't have to have that x term. Okay, so 2x squared minus 162 equals 0. Okay, so we're going to graph the corresponding quadratic function. Okay, I'll just do that on the graphing calculator. Okay, 2x squared minus 162. All right, and we'll graph that. Okay. I'll just go over to the settings tab here and just change the x-axis and make it, looks like it's about negative 20 and 20, so I'll just expand it a little bit that way. Okay, and so you can kind of see there what the quadratic function looks like. Okay, so we have two intercepts here. Okay, and so we can see that they're at about about 9, I think. Okay, I don't really have a way of verifying on here, but it looks like the intercepts are at 9 and negative 9. Okay, so if you go back and you look at the equation, you can verify that, right? Because 2 times x squared, that's 2 times 9 squared, or negative 9 squared. They both give you 81. So 2 times 81 minus 162 is 0. Okay, so we do know what the x-intercepts are. There are 2 of them. Okay, obviously only one of them makes sense in our problem, right? Because we're not going to have a negative width. But we know that x can equal 9, or it can equal negative 9. Okay, so from your graph, what are the roots of the quadratic equation? Okay, the quadratic equation roots are 9 and negative 9. And how do you know? Well, when you put them into the equation and substitute them in for x, you get your left side and your right side are equal, right? They make the equation true. And are all roots acceptable? No, okay, because we don't want to have a negative width. Okay, factor the left side of that quadratic equation. Okay, and you have to think back a little bit to foundations here, but you might remember that the first thing that you do when you're graphing is you're going to want to take out any common factors that are present. Okay, so you take out a factor of 2. All right. Oops, I did not want to do all that. Just erase. Okay. So x squared minus 81. Okay, and then when you look at that, hopefully you remember this well enough that you're going to see a difference of squares. Okay, because x squared and 81 are both perfect squares. So you should be able to just go back and factor that as x plus 9, x minus 9. Okay. All right, so if you factor that, graph the corresponding quadratic function in factored form. Okay, so I can take that same factored form in there, put it into my window here. So 2 times x plus 9 times x minus 9. Okay, put that in. and we'll say we're going to graph it. You'll see the red one, and then you'll see the green one right on top. Okay, so just to show, I guess, the factored form being the same. Okay, how is the factored form of the equation related to the x-intercepts? Well, you can see really nicely that when x plus 9 is, or when x is equal to negative 9, okay, that whole factor there becomes 0, the x plus 9 factor, so the whole function is 0. And the same with the second factor, or the third one, I guess, if you count the 2, x minus 9. When x is equal to 9, that factor also equals 0, which makes the function 0. Okay, so those factored forms are really useful because they tell you where those zeros are. Okay, and how can you use the x-intercepts of a graph to write a quadratic equation in standard form? Well, now you might have said, okay, I know my intercepts are x plus 9, x minus 9. Okay, and so if you had decided to go, if they were r and s, okay, if the x-intercepts are r and s, that means that your function is going to have as two of its factors x minus r and x minus s. Okay. Okay. So, I mean, that gets you part of the way to writing your function. Okay, but just so you know, there's going to have to be another constant value here that is multiplied by so you can truly get the shape of the function. Okay, and I'll just kind of show you that on the graphing calculator. Just show you that knowing the roots doesn't necessarily tell you exactly what function you're dealing with, and I'll just show for you one example of a function that has the same intercepts but actually has a different shape, and that's just due to the value of a. Okay, and so it'll change where your vertex is, right? It just doesn't change the intercepts. So if I graph those all in, I mean, you could do a couple, but you can see that that function there, I'll zoom out a little bit, has the same intercepts. Okay, but just by knowing the intercepts, you can't know exactly everything about the function. You do need to know a little bit more. Okay, next part of this is for men's sitting volleyball. A Paralympic sport, the length of the court is 4 more than the width. Okay, so if we let x equal the width, then the length is going to equal x plus 4. Okay, so then in order to write out our equation in standard form to represent the area of the court, we're going to have, I'm going to take x over length times width, so x times x plus 4, okay, equals 60. Okay, so to write it in a standard form equation, x squared plus 4x, okay, and then we would just subtract 60 from both sides, minus 60 equals 0. Okay, graph the corresponding function, quadratic function, and see how many x-intercepts there are. Okay, so I'll go back to this online thing, x squared plus 4x minus 60. Okay, get rid of those two. Okay, so how many x-intercepts are there? There are 2. Okay, it looks like negative 10 and 6. Okay, and obviously the 6 is the only one that makes sense. Okay, so if we were to use, so you can say that the intercepts are negative 10 and 6. Okay, use the x-intercept, x minus r and x equals r and x equals f of your graph in step 3 to write the quadratic equation. Okay, so knowing that my intercepts are negative 10 and 6, okay, I'm going to go back over here. Okay, so if I say x equals 10, sorry, x is equal to negative 10, right? X equals negative 10 and x equals 6 were my two intercepts, so it would go x plus 10, because that's x minus negative 10, so x plus 10 times x minus 6 equals 0. Okay, it says to write the quadratic equation that way, okay, and graph the corresponding function. So x plus 10 times x minus 6. Okay, so if I graph them both, you're going to see I'm going to get the same thing. And the reason for that, and I told you in that last one that you don't know everything, so you don't know if they're going to be exactly the same. But the reason for that is that there's no other number that you would need to multiply it by to get that answer or to get your equation right. And the reason for that is because in this case a equals 1. Okay, so basically you just get lucky here that when you take your roots 6 and negative 10, that it happens to be that when you multiply them back you get the same root, or you get the same function. Okay, because a equals 1. Okay, and I guess we're going to look at 5. Reflect and respond. How does the factored form of a quadratic function relate to the x-intercepts? Well, you can easily tell the x-intercepts from the factored form. Okay, so if it's x minus 6, then you know 6 is one of your intercepts. Right? If it's x plus 10, you know that negative 10 is one of your intercepts. Okay, those are also the zeros of the quadratic function. So what makes the function equal to 0? And the roots of the equation. So what values of the equation, what values of x make your equation true? Okay, describe how you can factor this quadratic equation, x squared minus 5x minus 6. Okay, the way that I would do that is, I would just want to, I don't know what you guys, I hope everybody's familiar with this method, but I would say what are two numbers that I would add together to give me negative 5, okay, and multiply to give me negative 6. Okay, so I'd be thinking of the factors of negative 6, okay, and so I would go negative 6 and 1, and actually that works pretty good. That's the first one that I thought of, and it actually does work. So negative 6 plus 1 equals negative 5, and negative 6 times 1 equals negative 6. So then I would say this could be written in factored form as 0 equals x minus 6, x plus 1. Remember, when you put them back here, you want to match the sign of those numbers that you put in your blanks. And so then I would know that the roots are going to be x equals 6 and x equals negative 1. Okay, so if I were to graph that equation, I would find that it crossed the x-axis at the values of negative 1 and 6. Okay, if the roots of a quadratic equation are x minus 3 and, are 3 and negative 5, then I could say a possible equation would be found by going x minus 3 and x minus negative 5, or x plus 5. Then if I wanted to, I could multiply that. Okay, 5x minus 3x, so x squared plus 2x minus 15 equals 0. That's a possible one, but anything, if you took that equation and multiplied it by any constant number, that would give you some other possibilities as well. Okay, so there are a number of different possibilities, but that's one of them that would definitely have that, have those roots.